Ever wondered what would happen if you could go back in time and prevent your grandparents from meeting? This provocative idea is the starting point for our journey into the fascinating world of time travel and its paradoxes. Time travel, an intriguing concept that has captured the human imagination for centuries, challenges our understanding of the linear progression of time. But what if you could bend the rules? What if you could revisit the past and change it? This brings us to the grandfather paradox, a thought experiment that delves into the consequences of altering the past. The paradox is named so because it presents a scenario where a time traveler prevents his grandparents from meeting, thus preventing his own existence. It's a mind-bending puzzle that intertwines cause and effect in a seemingly impossible loop. So, the grandfather paradox poses a rather intriguing question. If you alter the past, how does it affect the future? Understanding the grandfather paradox isn't as complex as it may sound. Picture this: you've got your hands on a time machine. You decide to travel back in time, say 60 years or so. There you encounter your own grandfather, a younger version of him, of course. Now what if, for some reason, you prevent him from meeting your grandmother? You've effectively changed the course of history. But here's where things get tricky. If your grandparents never meet, one of your parents won't be born. And if one of your parents isn't born, well, you can see where this is going. You won't be born either. But wait a minute. If you were never born, how could you have traveled back in time to prevent your grandparents from meeting in the first place? It's a loop that seems to have no beginning or end, a true paradox. This, my friends, is the essence of the grandfather paradox. The grandfather paradox is a theoretical predicament that arises from the concept of time travel. It's a classic example of a situation where changing something about the past creates a contradiction in the present. But how can this be? After all, we live in a universe where cause and effect rule supreme. The paradox brings to light some very perplexing questions about the nature of time and reality. If the past, present, and future are not as linear as we perceive them to be, then the concepts of cause and effect as we understand them could also be flawed. But you might ask, what if the universe has a way of preventing such paradoxes? Sure, some theories suggest that the universe could correct itself to prevent paradoxes like a cosmic autocorrect. However, these are just theories. The truth? Well, we don't really know. In essence, the grandfather paradox challenges our understanding of time and causality. It forces us to question the very fabric of our reality and confront the possibility that our understanding of the universe may not be as complete as we'd like to think. The grandfather paradox is not just a quirky thought experiment, it's a window into the mind-boggling world of time travel and theoretical physics. Quantum mechanics might hold some answers to the paradoxes of time travel. Delving into the realm of the minuscule and the abstract, quantum mechanics introduces us to a world where particles can be in two places at once, and cats can be both dead and alive. This peculiar concept is known as quantum superposition. It's like having a coin that's not just heads or tails but both at the same time, until you observe it. Now consider applying this principle to time travel. The grandfather paradox hinges on the premise that a single action, like eliminating your grandfather before your father's birth, would prevent your existence. But what if, in the quantum world, you could both kill and not kill your grandfather simultaneously? This is where the idea of quantum superposition comes into play. In a quantum state, your grandfather would exist in a superposition. He'd be both alive and dead, until the state is observed or measured. This means that you, as a time traveler, could exist and not exist at the same time, until the superposition collapses into one state or the other. In this scenario, the paradox seems to resolve itself, as both possibilities could coexist, until observation forces reality to commit to one. The quantum world is a probabilistic one, where multiple outcomes can exist side by side. But here's the tricky part. We don't yet have a fully developed theory of quantum gravity, which would reconcile quantum mechanics and general relativity, and thus, fully explain how time travel might work on a quantum level. To add another layer of complexity, there's the concept of quantum entanglement, where particles become linked, and the state of one instantaneously affects the other, no matter the distance. Could time-traveling particles be entangled? Could this entanglement resolve or further complicate our time travel paradoxes? While quantum mechanics may not provide a definitive answer, it certainly adds another layer to our understanding of time travel paradoxes. Theoretical experiments can provide fascinating insights into the grandfather paradox. Let's delve into the realm of thought experiments to understand this paradox better. One proposed experiment involves a game of billiards. Imagine you're a time-traveling pool shark. You hit a ball, it zooms into a time machine, travels back a few seconds and knocks its past self out of the way. The past ball never reaches the time machine, hence no future ball comes back to deflect it. It's a clear contradiction, right? But this experiment, proposed by physicist Igor Novikov, actually suggests that such circumstances are impossible. It's known as the Novikov self-consistency principle, stating that any action taken by a time traveler or a time-traveling object must be self-consistent, meaning it can't prevent its own existence. Another theoretical experiment involves the concept of quantum superposition. This experiment, proposed by David Deutsch, a physicist at the University of Oxford, suggests that a time traveler could both kill and not kill his own grandfather. Sounds confusing? Well, quantum mechanics often is. Deutsch suggests that time travel might follow the rules of quantum mechanics, meaning the time traveler would enter a superposition of states. In one state, he kills his grandfather. In another, he doesn't. This means the timeline splits, and both realities can exist simultaneously. However, these experiments are not without limitations. They remain theoretical because we lack the technology and understanding to test them. Novikov's principle, for instance, is criticized for being more of an assertion than a provable theory. Deutsch's experiment, on the other hand, is based on an interpretation of quantum mechanics that is not universally accepted. These experiments, while theoretical, challenge us to think critically about the paradoxes of time travel. They propose that the universe has its own rulebook, one that ensures its consistency and continuity. So, while we may not be packing our bags for a time-traveling adventure just yet, these thought experiments allow us to journey into the fascinating complexities of our universe, right from the comfort of our armchairs. Science fiction has long been fascinated with time travel and the grandfather paradox. This genre has wielded the paradox as a narrative tool, transporting us to worlds where the rules of time are bent and reshaped. It's through these imaginative narratives that we can explore the complexities of the grandfather paradox in a relatable and engaging way. Some of the most beloved science fiction tales grapple with this paradox. These stories often depict characters who journey back in time, inadvertently altering the course of their own existence. They ask the question, what happens if you change something in the past that directly affects your future? Consider the classic tale where a character travels back in time, preventing their grandparents from meeting, thus negating their own existence. This scenario presents an intriguing quandary, doesn't it? If our time traveler doesn't exist, then who traveled back in time to prevent the meeting? Such narratives not only entertain but also provoke thought, encouraging us to ponder the intricate web of cause and effect. They illustrate the paradox's inherent contradiction and invite us to grapple with the implications of altering the past. Science fiction doesn't always provide answers to these paradoxes, but it does offer a unique lens through which we can explore these profound concepts. It's a testament to the power of storytelling in unraveling the mysteries of our universe. Science fiction not only entertains us, but it also expands our thinking about complex concepts like the grandfather paradox. What role do wormholes and black holes play in time travel paradoxes, you may ask? Let's dive right in. Wormholes, hypothetical regions of warped spacetime that provide shortcuts through space, are often proposed as a possible route for time travel. If one end of a wormhole was kept stationary while the other was moved at near light speed, time dilation could theoretically allow for travel into the future or past. Now, onto black holes. These celestial bodies with immense gravitational pull distort time as well as space. Near a black hole, time slows down relative to further away, an effect known as gravitational time dilation. In theory, a journey into a black hole could, under very specific conditions, serve as a one-way ticket to the future. However, these methods of time travel could either resolve or exacerbate our paradoxes. A wormhole might allow for the existence of a closed, time-like curve, a path through space-time that loops back on itself, potentially enabling the grandfather paradox. On the other hand, the extreme conditions near a black hole might prevent any paradoxical situations by simply spaghettifying any would-be time traveler. While the practicality of using wormholes and black holes for time travel remains uncertain, the theoretical implications are intriguing. As we continue to explore the cosmos and the nature of time itself, we may yet find answers to these paradoxical questions.